Okay, hi everyone. Hope we all had a very productive morning debugging Catbook. I saw a lot of really good thinking going on. Anyways, today we're going to be talking about databases. I'm Annabelle, and
I'm Sophie.
yeah, so let's start with a quick introduction to what databases are. So currently the way that we are storing data in Catbook is that when a client sends a request and they ping like the API/story endpoint, for example, like trying to write a new story, this is sent to the server and all our data is stored directly on an array called stories in our server. So this is going to add a new story directly on our server. So here's like the code in api.js right now, right? We have like this data object that has the array of all of our stories with fields like ID, creator name, and content. But there's a couple of issues with storing data in our server just as a variable. And you might have already encountered some of them or have already like an idea of what some of the issues might be. So let's say everything is fine and we're all good, right? We're posting stories on our Catbook. You guys are like busy debugging or whatever. The clients are pinging the API/story endpoint. And then our stories object is being updated accordingly, right? So we're adding the hi, hello. But let's say, oh no, our server crashes. So our server is down for some number of unbearable hours. And let's see what happens if once our server comes back up, all of our data is going to be lost inside the stories array. So everything that was just sent is now gone. And obviously, we don't want this, right? Like we don't want all of our data to just be gone if the server crashes. And it's not just if the server crashes. If we close our terminal or if like your laptop runs out of battery, then all of your data will be gone and all the stories that you just posted are not going to persist on Catbook. And you can imagine that with any web application, you want your data to persist and you want to be able to retrieve and display the data that your users have previously submitted, even if something crashes. The other thing that happens is, let's say our server never crashes and it's some like super powerful like mega server. But Catbook has a lot of users, right? Like all of you guys are already using it in class right now. And this is going to lead to a lot of RAM issues because that's going to be a lot of memory and we're storing like hundreds of gigabytes of stories and comments. So this is also kind of an issue. So we want to store our data permanently. And so one of the other ways, the alternatives that we have instead of storing the data directly on the server is that we can use a text file and we can store this text file on our hard disk instead of storing everything directly on the server. So this seems more permanent, right? We also have like functions that we can use to access and send data to our text file. So if we want to load data, we can use read data from file, which if you guys have taken like 608 before, you've probably seen it's like a very basic like read data function. And basically this is just taking in what we have in our data.txt file and reading that. And then if we want to save data to data.txt, we can use the function write data to file. So here's how we would implement it, for example, in like our API, in our API endpoint. And this is if we wanted to like load the data from the file. So you might be thinking, yay, we solved the problem. Now we are like storing everything in this text file on our hard drive and it's all good because now it's like permanent, but there's still a couple of issues with this. So what's wrong with data.txt? Does anyone want to take a stab at just like one problem that they can potentially think of? Yes. Yeah, exactly. So one of the big issues is if we're looking up things, it's going to be extremely slow. So that's like one of the issues I'll talk about later. But some of the other issues we have are also like kind of like adjacent to what you mentioned is if we're saving stories and comments, the write speed is also going to be very slow because we have to call that function every single time. And you can imagine that's going to be very tedious and slow. The other thing is, you can imagine we're still keeping everything in our RAM, so we can still run out of storage on our hard drive. So it's kind of similar to the problems we had before, like if you run out of storage in your RAM, this is still like an issue. Also, this is like what you were saying, right? The query speed is very slow because like if we want to just return one story posted by like a given user ID, right? We have to linear search through every single one of the stories, and this can be very, very slow. Also, your laptop hard drive can still break. It's not immune. You can like drop your laptop in a pool or something. Like this is not fail proof. Also, if two users post at the exact same time, we don't actually know what ends up getting stored in data.txt because we don't know like which user's request was actually fulfilled to like write data to the file. So that's kind of scary if we don't know what's being saved in data.txt. Now, how do we fix all these issues? Well, we have this really cool thing called databases. Yeah, so there's like SQL databases, and then also like MongoDB, which is what we're going to be using for our web application, which Sophie is going to talk more about later. But basically, SQL databases are like really good for like relational data and like very structured data, but we're going to use MongoDB because it's a little more flexible for our purposes. Basically, a database is just a really organized collection of data, and it's a way to store all of the data that you're going to be handling in your application in like an organized manner. A database management system, DBMS, is basically a collection of functions that lets you perform operations on your data from your database, like retrieving data, adding data, modifying it, deleting it, etc. So our database is basically like our substitution for data.txt, but much better, and we'll talk about the reasons why in a bit. And the database management system is very similar to the read-write data from file functions that we just talked about earlier, but also better, and we'll also talk about why. So there's a lot of different types of databases, but we're not really going to get into it. If you're interested, you can like do more reading on your own. But some cool examples, I think, are like graph-based databases, which show kind of like really emphasize the relations between data, and also time series databases like InfluxDB, which shows like time-stamped data. So it's really useful if you're trying to track things over time. And then hierarchical databases like IBM IMS, which shows everything in kind of like a tree structure. So it'll show relationships using like nodes. So that's cool. Anyways, now Sophie is going to talk more about how we can perform different operations with our databases.
Yeah, so we just went over how we're going to replace data.txt with a database, and we're going to replace our read and write functions with a DBMS. So let's talk a bit more about the reads and writes through the DBMS. So yesterday in workshop 3, we talked about how we can make a GET request from our front end to the /API/comments endpoints to request comments from our server. And by doing that, our backend server is going to send the comments back to the front end. So what actually happens in the backend if we now have a database Is this better? Test. Okay. So let's talk about what actually happens in the backend server. So after we make the API request to the backend server, our backend server can call a read function through the DBMS, and the DBMS is going to go to our database, gather all the stories from the database, send it back to the server, and the server can now send that back to the front-end client. So similarly for writing to the database, if you remember in workshop 3, yesterday we learned how we can make a post request to /API/comment in the backend server. And what this does is we write a new comment to the backend server, and now the backend server is going to store it in the data variable and tell our front end that it has been successfully posted. So now let's take a look at what happens in the backend with our DBMS database system now. So similarly, our server is going to call a write function, and through this write function, this DBMS is going to take the new story and add it to our database. So let's take a look at some pseudocode for read and write functions to our DBMS. So typically, our DBMS is going to be a package that we'll want to import into our backend server. And one operation we can perform is a read. We could read all of the stories in the database. Okay. Another read we can do is with a query. We could filter the database for certain stories that we want. So in this pseudocode, we'll be filtering for all the stories with ID 4, and that'll just be one story since an ID is a unique identifier for each object in our database. We can also do a write, as we're familiar with yesterday. And we could also delete and delete by a query. So this example might delete all the stories posted by a certain user named Joyce. We could also update a story that's already been written to the database, and this would make an update to stories with the author J. But yeah, this isn't real code, so don't try writing it in your backend server. So let's talk about what types of databases we might use. So the common example of storing data you might be familiar with is through like Excel and Google Sheets, and usually you'll be storing data like in a row column format. So a relational database, in a relational database, each spreadsheet is called a table, and you'll have rows and columns for categories of data. So for our Capbook example, you might want a users table showing all the users using your app, and also maybe a stories table showing all the stories being posted for your Capbook app. And you'll have relations between the users and stories. For example, in the stories, you might want a column showing the user IDs. So for each story, which user is posting the story. And but for a relational database, you'll need to write overhead code for dictating the relations between the users and stories table as shown here. Some example of relational databases is SQL, which stands for Structured Query Language. So we have some problems with this. In the table shown earlier, the data for one user is spread out across multiple tables, and as your web application gets larger and you'll want to be storing more data, this can get really complicated because you'll have to write overhead code for any relationship between tables. So this can make our code hard to understand, and as your web app gets larger, it'll make adding features a lot more difficult. And as I mentioned earlier, you'll need overhead code for dealing with the relations between tables. So as a programmer, we'll have to write all the code to accommodate the structure of our database, and that's bad. We want our database to adjust to the needs as a programmer and have it be flexible for adding new features and data. So instead of thinking about our data in terms of rows and columns, we can think about a piece of data as an object, as we're already familiar with. So this is called a document database. Instead of storing your objects in rows and columns, we can think of an object with all the fields as a document. And this is very similar to JSON objects that you've been working with in Capbook already. And documents don't need to have the same fields, so this allows for a lot of flexibility. So for example, this is what a document database might look like for the example earlier. But in this example, the object for Annabelle's user object doesn't have any content. So you can have very flexible fields, but as we'll see later, you might want a structure for your fields, and we'll talk about how we can do that in the backend. So back to yesterday's workshop 3, we were working with comments that look like this, and as you see, this has the same object layout that a document database will be using. So it's a lot more natural and intuitive to work with as a programmer rather than working in rows and columns. So the specific document database we'll be using is called MongoDB, and this is a document database that stores data in JSON-like documents. So you have documents which represent each object in a collection of data, and maybe you'll want very similar looking documents that live in a collection. So you might want all your comment objects, which are now called documents, to live in a comment collection. And similarly, you might want a stories collection containing all of your stories documents, which are alike JSON objects. And you want all of your collections to live in a database, which will correspond to all the data you want to hold for your web application. So we might have a Capbook database. So now, instead of having a text file that lives on our hard drive, we could use MongoDB and the corresponding database management system. So this optimizes our write speed because a lot of engineers at MongoDB have thought about this and thought about ways to optimize it. We're also optimizing our memory usage because we're no longer storing all of our data in a variable in our server. Query speed and concurrency issues are also solved thanks to engineers at MongoDB. As a reminder, earlier we were storing all of this data as a variable in our server, so that takes up a lot of RAM. But there's still one more issue. Our hard drive could still break. We want to make sure that our web app is foolproof so that any fault we might encounter is tolerated and doesn't interfere with the with how our web app operates and how our users use our web app. So how do we make storage of our database fault tolerant? Does anyone have an idea? Yeah. Yes. The naive solution is redundancy, and that's exactly what MongoDB does. It duplicates data across different hard drives so that in case any one fails, we can just access a different hard drive that contains all of our data. So MongoDB Atlas does this for us. Instead of storing our database on our computer's hard drive, we can use MongoDB Atlas and store it somewhere over the cloud. And this makes our life easier. We no longer have to deal with running the database on our laptop and dealing with problems in case it breaks. The database is managed for you by MongoDB Atlas, and you can also share your data with your teammates as you're working on your WebLab project. And this is a lot more reliable than your laptop's hard drive because it replicates your data. So now your backend server is going to store your data over the cloud. And what this looks like is it'll be accessing a primary MongoDB instance on one hard drive, and you have replicate sets of this instance. So in case the primary MongoDB dies, the hard disk breaks, you can access a replica set. So let's take a look at the MongoDB user interface. So if you have, here's a catbook database, and in it I have comments, stories, and users collections. Right now I have the stories collections clicked, and inside the stories collection I have different documents. These look like JSON objects, and they have different fields. And if you're working on making some data, like Mickey Mouse data for your web application later on for your WebLab project, you can just edit fields and directly from the MongoDB interface and add new documents. So let's put everything together. When we make a GET request, the front end code is going to send that request to the back end. And it's going to make it to the API stories endpoint if we're trying to read stories data. And now the back end, instead of sending data from the stories file, it's going to call the DBMS, which is going to go to the database, find all the stories. The database is going to send this back to the back end, which can send it back to the front end as we went over yesterday. Similarly, we can now make post requests to create, update, or delete data. So the front end, maybe your user is making an edit to their story or adding a new story. The front end will make a post request to the /API/stories endpoint. The back end receives this request. It's going to call maybe some write function or delete function via the DBMS. And now it can perform the operation in the database. So in summary, rather than storing data on our server or in a text file, we'll be using a database to store our data. And the specific database we'll be using is a document database called MongoDB. And specifically, instead of running MongoDB on our hard disk to make our database more fault tolerant, we'll run it over the cloud using Atlas because Atlas automatically has redundancy for us in case the primary MongoDB hard disk breaks. So after lunch, we'll talk about how we can... Okay. So now we'll talk a bit about MongoDB specifics. Feel free to leave some feedback for the Intro Databases lecture. Yay, okay. Yeah, okay. Now we'll talk about MongoDB specifically. What is MongoDB? So as we just mentioned, it's a document database that allows our JSON objects to be stored directly in the database like we're familiar with. So here's an example of a JSON object. There's 3 fields: a name field for my name, Sophie, my age, which is a number, and my hobbies, which is an array of strings. So these are examples of objects that might be stored in the database. So why are we using MongoDB? So it's efficient when we need to write a lot to the database, a humongous amount. So actually, Mongo is an abbreviation for humongous, and it's also useful for when the structure of our data is very prone to changes, because just as we talked about, the fields allow us a lot of flexibility because we can add new fields or change the amount of fields in a document. And it's relatively easy to use as a programmer because it's very intuitive in the object-oriented nature. So let's talk a bit more about the structure of MongoDB. So in each object, we might have fields to describe the object. So maybe we'll have a field describing the color, length, or how poofy or how angry our object is. I've been calling it a corgi, but apparently this is a Shiba. Yeah, okay. And we'll have documents which correspond to each object. So inside the document, we have fields, and this document might correspond to a corgi. And we might have a collection of corgis which might look like Oh, by the way, I'm trying to make a parallel to a warehouse. So paralleling to a warehouse, a collection might be a crate of corgis, and a database might be a bunch of crates, which are collections. So your database might hold a bunch of different types of collections, which each have different objects in them. And a MongoDB instance might be like a warehouse of storage units. So to reiterate in words, a MongoDB instance is a group of databases that live on one server. And remember that we have replica sets of MongoDB instances. A database lives inside your instance, and it usually corresponds to one web application and holds all the data you want to store for that web application. And a database might have a bunch of different collections, and each collection is a group of very similar pieces of data. So maybe we'll want a collection for our stories, a collection for our users, a collection for our comments, and etc. Inside each collection, we're going to hold many different documents which we want to have similar structures. So maybe in our stories collection, we want all our documents to share similar fields such as name, content, ID, and yeah. So here is a diagram of the structure of our storage facility. And also, this is a sneak peek of the prizes we'll have at our hackathon, or giveaway prizes. So make sure to come. And this corresponds to these MongoDB objects. Yeah, okay. So if you have any questions, feel free to drop them in weblab.mit.edu/questions. So remember, we talked about why we're using MongoDB, and it's because it allows our databases to be very flexible compared to a SQL database. So this means that different documents in the collection can have different fields, as we just went over. So here's an example. So say we have a corgi collections with these 3 documents, a document for 3 corgis named Sophie, Annabelle, and Abby. All 3 of these documents have the name field, but you notice that they shared the other fields that they have, they don't share. But if we're working on a web application, we might want all of our documents to share the same fields in a collection. So what if we want to enforce the same structure for all documents in a collection so that all of these corgi documents have all same 5 fields with the same type for their value? We can use Mongoose. Mongoose is an object data modeling JavaScript library that we'll use in our backend server that will allow us to enforce a structure for the documents in our collection. So fun fact, a mongoose is also a mammal, and the plural is mongooses, not mongoose. Okay, so what is Mongoose? Mongoose is a JavaScript library that we'll use in our backend server, and it allows us to interact with MongoDB. It allows us to enforce a structure for our collections from the very beginning. So once we start making post requests and get requests to our database, they'll already have this structure. So what does Mongoose do? It connects to the MongoDB cluster, which we'll cover code for in the workshop. It enforces schemas and models, which dictate the structure of the documents in the collection. It allows us to create documents by having functions that kind of parallel the DBMS, and that allows us to interact with the database with create functions, read, updates, deletes, and more. And I think we'll end here.